So now question 9, okay? Why is ammonia considered a base? Whoops. Why is ammonia considered a base? So actually, for this, because ammonia almost has no relation between name and compound, you just have to kind of memorize it, okay? And I'm sure you've seen ammonia quite a bit in terms of like when it's written, okay? Ammonia is specifically NH3. That, let me just write that better. That was bothering me. The N didn't connect. Oh my gosh. Oh well. So NH3, okay? That is ammonia, right? Now to figure out why it's a base, okay, we want to be able to write it actually in its Lewis dot diagram, because that way we can actually see how it classifies as an acid or a base. But this question is supporting that it's most likely going to be a base, and I'll show you why, okay? So nitrogen, not only is it in the 15th column, okay, but when you also do its electron configuration, you'll see that you start first with helium, okay, and then for this valence shell it'd be 2s2 2p3, okay, indicating it has 5 valence electrons. Hydrogen, funny enough, is just going to be 1s1, so there's 1 valence electron for every hydrogen, so it'll be 1 times 3 and 5, so we have to in total account for 8 electrons, okay? And so for the Lewis dot diagram, let's just put the nitrogen because it's the least in the middle, and it's going to be bonded to 3 hydrogens like that, okay? And now for the last one, actually, we have to fill the shell. So nitrogen fulfills the octet rule, and hydrogen is completely fine with just one bond. And if we did the electron number to find that electron number, right, it'd be same, that 5 valence electrons minus how many lone pairs it has, which is 2 electrons in its lone pairs, plus the amount it's sharing in its bond, so it'd be 6 divided by 2. So 2 plus 6 over 2, that's 3, so that's 2 plus 5. So exactly, nitrogen is satisfied, and hydrogen, 1 minus 0 plus 2 over 2, okay, that is 1 is, well, 1 minus 1, we got 0 as well. So this is completely how it wants to be. So now, what do you notice right away? That NH3 has a lone pair, okay? So the definition of a Bronsted-Lowry base, okay, is that it has a lone pair that it can use to attack and take a hydrogen. So what happens here is that as there's I guess not even just a hydrogen, specifically a proton. So as there's H plus, quote unquote, floating in the water, this lone pair will actually attack this to where you would now have, because there's also a positive charge in that H, okay, it would attack it to where now we have this, okay, with the positive, near the middle to account for it. Considering now that, if we redid the number, it would be now 5 minus 0 lone pairs minus 8 over 2, okay, it was plus 8 over 2, so that's 5 minus 4, which is 1, hence why we have the positive charge on the nitrogen. So that was what we get when that lone pair attacks that hydrogen. Now you're probably wondering, why would it want to go from a stable 0 to a positive charge? Its summary really is because of how much hydrogen bonds play a role in it. Hydrogen bonds are so powerful that in terms of like the cost and loss of energy, is that nitrogen is willing to give up that charge to be able to make sure that it has as many hydrogen bonds as possible when it comes to at least ammonia reacting with excess protons in a system, okay? So if we were to, so now we've shown that in a sense with the Bronsted-Lowry definition of a base is that because it has a lone pair, it's able to take a hydrogen. And remember, bases accept hydrogens, which makes this, okay, a base. Okay, that's why ammonia is considered a base. And if you're actually to write down the whole formula to where it was attacking, forming that H plus, it'd be kind of like this: NH3 plus, let's say, water, right? Because that's an example as well of a double bond as well that it wants to kind of tackle. I mean, not double bond, a hydrogen bond, which is why it's quite competitive. So that nitrogen will try to, in a sense, attack one of the hydrogens on the oxygen. Okay, and so now we have NH4 plus OH minus. Okay, so as the rules as well state, we have this one that received the hydrogen, so this will be the conjugate acid, and this one would be the base. Okay, and in this case, water lost a hydrogen, so this would be the conjugate base. Okay, and this would be the acid. So in both I guess explanations, the NH3 still serves as a base. So that's why in total ammonia is considered a base. And now you're probably wondering, oh, can't ammonia give away any of the other hydrogens? So here's where I guess in a sense why it can't. As I've shown you this NH3, right? It really likes its hydrogen bonds, okay, and it wants to have as many as possible, but you know, within keeping its electron number. If I got rid of a hydrogen, so if you for some reason had NH2 minus, right? Okay, not only now does it, like, it will be shown like this, it'll be 2, it'll be like that, and there would be a minus on the nitrogen. Not only would it have less hydrogen bonds, which it personally doesn't like, it's even its electron number, if you did the math, it'd be 5 minus 4 now, because there's 4 electrons in this lone pair, plus 4 over 2. So it'd be 5 minus 6. So it'd be minus 1, okay? So now it's lost a hydrogen and is also off balance in regards to its charge. It really gained literally nothing. So it would never, well, rarely actually want to give up a hydrogen to, I guess, form NH2 minus, okay? Because it just doesn't gain anything. Here, when it goes to the NH4 plus, right? At least it got an extra hydrogen bond to make up for the fact that its charge is now no longer a 0. It wants to get as close to 0, right? But now, when it comes to NH2, it is now no longer 0, and there's less hydrogen. So it really lost in every sense. Hence why ammonia would not be giving up its other 3 hydrogens there, okay? So exactly, we have here Bronsted-Lowry base accepting the proton, which is what we have, and so it forms a new species called the conjugate acid in this case for the ammonia, and exactly because it reacts with water to form NH4 plus, hence it's a base in all accounts. Okay, so this is correct. So now we're on to question 10.